Good day to you from Chem Help ASAP. In this video we will perform an electrophilic aromatic substitution, specifically a bromination. The video description contains links to supporting documents, including the laboratory procedure and proton NMR spectra. Here we have a model aromatic bromination. The key reagent for this kind of reaction is an electrophilic source of bromine, Br+. To show this reagent in a general form, I've written Bry. That's supposed to represent bromine attached to some leaving group, Y. Two examples of these types of reagents are shown below. On the left, Br2 with FeBr3 is the classic example. FeBr3 is a Lewis acid that binds Br2 and essentially puts a great leaving group on Br. Nucleophiles are then more likely to attack the end Br. N-bromosuccinimide, or NBS, fits this same profile. With a little bit of acid, a carbonyl on NBS can be protonated. That makes bromine more reactive to be attacked by nucleophiles. On the screen is our reaction for this experiment. We react this molecule on the left that's acetanilide with NBS in acetanilide and a catalytic amount of HCl. The result is a bromination of the ring through an EAS reaction, electrophilic aromatic substitution. This particular EAS is helped by the amide nitrogen, which is an activator and ortho-para-director. We'll perform this reaction on a 5 millimole scale. Approximately 5 millimoles of both the acetanilide and NBS with 10 milliliters of acetanilide. The product, 4'-bromo acetanilide, will precipitate out at the end when we add water. Filtration will give us the crude isolated product. Fortunately, the crude product will be quite clean. Normally, I like to record weighing out the reagents. I tried to for this video, but I had the camera in picture mode instead of video mode. Here is one of the pictures I took. I thought I was stopping recording at the end of weighing. Instead, I got a quick snapshot of both reagents on weighing paper. On the left is the NBS. That is 896 milligrams, a speck more than 5 millimoles. On the right, and still on the weighing paper, is our acetanilide. That is 676 milligrams, again very close to 5 millimoles. Now let's set up this experiment. Fantastic. So we are ready to get started, and we're going to begin this reaction by pouring in about 10 milliliters of acetanilide into a 20 milliliter scintillation vial. I do have a stir bar in here. I'm going to get that going. Perfect. Now next I want to add the NBS, and this is the NBS, the N-bromosuccinimide, that we weighed out on the balance. And now that is stirring, and we're going to let this stir for just a little bit. I want to let all this dissolve that will dissolve, but it does, it's fairly crystalline because it's recrystallized, so it's pretty pure, and we're just going to give a few minutes and let that fully dissolve, and then we'll go ahead and add our next reagent. Okay, this has been going,
and it has been dissolving. I know it looks like it's virtually, there's just a speck in there. I think it's good enough. Now let's go ahead and add our next reagent. This is acetanilide. This is what we are brominating. We can mix this in just at room temperature. And let's turn up the stir a little bit, really get things agitated and suspended. I'm not sure how well it shows up on camera, but that yellow's just a speck. Not a lot, but that is just a little bit yellow. Now, this is, I think, done about all it's going to do. And so we have one more thing to add in here. And that is 1 drop of concentrated HCl. So I have a bottle of acid off the screen, and I'm just going to drip in 1 drop and watch what happens. So immediately yellows quite a bit, and things are happening. And let's just observe for a little bit what we're seeing. So by adding the acid, we are, in part, we're probably doing a lot of things, but one thing that can happen is we are protonating our N-bromosuccinimide. And as we protonate the N-bromosuccinimide, we are activating it. We are making that bromine a stronger electrophilic source of Br. And the consequence of that is it makes it more reactive. And as it's made more reactive, we are going to start getting a faster rate of reaction. So we'll let this stir a little bit. I believe we'll see changes shortly, but I'm going to just let this stir off camera, and we'll come back once something has happened. So we've now waited about 10 more minutes, and you can see that we have plenty of solid here. I didn't monitor it for that full 10 minutes, so I can't tell you if that solid formed in 1 minute or 9.5, but I think it was less than 9.5. So we got some solid formation. That's great. That is our product. We're going to let this stir for perhaps another 10 minutes, and then we'll move on to the next steps and actually start to finish up this reaction. This has been stirring now for another 10 minutes. I don't think there's been a huge amount of change, if any, but we definitely have solid present, and that's a good thing. I had an old lab mate who would say precipitates and color changes are almost always good signs, and we've got a little bit of both, so my old lab mate would really enjoy this. So I'm going to go ahead and add some water, and the idea is by adding water we are going to dilute the acetonitrile. We're going to make it more and more polar, and hopefully that will help complete the precipitation of this product. So I'll add this in a little bit slowly. I don't know if I'll get all 10 milliliters in there. That's going to be kind of full up. That's good. We certainly affected the color a little bit by doing that. That looks great. Always nice to feel if we're getting any temperature changes as we do that kind of thing. I think those chunks are definitely some product. And to help things out, a little cooling is never a bad idea. So we'll add water and we'll cool this and let this sit on ice, and then we'll see if we can see what we think. If we don't think that we've precipitated everything, we can always dilute it into a greater volume of water. And if we do like what we see, we can go ahead and filter it as is. So we'll just see what another 10 minutes on ice lets it look like. After about 10 minutes on ice, this is what we're looking at. I think it looks pretty good. All of our yellow color has gone away with the water, which is interesting. I'm not sure why that is, but it wasn't really darkly yellow to begin with. So I think this is going to be adequate to go ahead and filter, and we'll see what we can recover out of this mixture. Well, anytime we talk about filtration, we're often talking about a vacuum filtration, so we need a Buchner funnel and a vacuum line to a sidearm flask. So here's our Buchner funnel. We're going to wet our funnel and seat this paper. And I'm going to use water. I'm going to treat this acetanitrile water solution basically as pure water. So I think that'll be fine. So we can seat our paper with water. Now here is our mixture. Tell you what, this is just a little bit off camera. Let's let the stir plate get everything suspended for us. Good, and now we'll go ahead and do our filtration. Great, great. We need to do some rinsing, because that is not going to cut it. Rinse a little more. Now we don't want to use too much water. Glad we have a trap on this. We're sucking some into the vacuum line. Okay, good. And that's it. It is all transferred. You see we're getting a little bit of additional precipitation down here. Yeesh, maybe a lot. Well, I tell you what, let's go ahead and let's talk about a mistake that I might have made, and then but we'll figure out how to fix this mistake. Okay, I kind of cut off that previous video quickly because something was happening that in hindsight doesn't surprise me, but it was not what I was expecting at the moment. And so over to the right we have our filter flask from before, and look at that, we got a ton of solid in there. So why did that happen? I was filtering it. The filtering is supposed to remove the solid, and yet we got a bunch of solid. Well, here's what happened. I went ahead and took our original reaction mixture. I added water to precipitate the product, cooled it down, and then I filtered it. Well, this happens sometimes. I didn't have enough water. I didn't dilute it with enough water, so I didn't get complete precipitation. So I filtered the material and then used additional water to rinse it, and then with the additional water the polarity increased, and now more product precipitated out, and it precipitated down in the bottom of the filter flask. That happens. That happens because sometimes you don't fully understand what's happening. It happens sometimes because you were too lazy to make sure everything had precipitated in the first place, which may or may not be what I did. But anyway, now we have all the solid. That looks like quite a bit to me. So we need to filter this. So we've done a filtration. We've observed precipitate in the filtrate, the original filtrate. So now we're just going to refilter. Now I have the original solid we collected over here. That looks great. But I want to see what's over in here. So I've set up another sidearm flask, and I have seated the filter paper with water. I have the vacuum going, so let's go ahead and filter the stuff that we filtered before and then precipitated a lot of product into. These things happen in lab. I wouldn't boast about it, but hey, when things go wrong, you go ahead and do your best to fix them, and that's what we're doing now. And hopefully we won't precipitate anything else down here. Okay, that's looking better. Good, good, good. Now, as is very commonly the case, when you see product collecting in a filtrate like we did in this flask, it looks like a lot. Sometimes it's not nearly as much as it looks. And we'll see that when we weigh things out, because we do have some product in here, but it's hard to tell on the camera. That's not exactly gobs and gobs of material. Still, I'm glad we collected it. Now we know, hey, the yield we got is the yield that we got, and we didn't lose a lot of material by just ignoring material that precipitated in the filtrate from the first filtration. Okay, so that's our isolation. These products need to dry, and pretty soon we'll get a mass on them once they are dry, and we'll take a look at the final yield and see what we got from this bromination. Alright, so the reaction is over. I filtered the compounds. Here they are spread out on a watch glass. They are nice and dry. Notice that this second crop Actually came off the filter paper in a sheet. Kind of interesting. But they are dry now. The first crop of crystals that we recovered had a mass of 806 milligrams, and the material on the left had a mass of, the second crop had a mass of 123 milligrams. That's a total of 929 milligrams from both batches. So that's actually a fairly nice recovery. We'll go through the calculations here in a second.
Let's figure out our yield. Here is the reaction scheme again. We know that we used 896 milligrams of MBS based on a molecular weight of 178 grams per mole. That's 5.03 millimoles of MBS. We used 676 milligrams of acetanilid based on a molecular weight of 135 grams per mole. That is 5.01 millimoles. Since these reagents react in a 1:1 ratio, the acetanilid is the limiting reagent. The limiting reagent determines our theoretical yield. So, 5.01 millimoles is our max yield. So, at most, that's how much 4' bromoacetanilide we can get. Fine, but what did we actually get? Well, we obtained 929 milligrams of product from our 2 crops of crystals. The molecular weight of the compound is 214 grams per mole. Therefore, we obtained 4.34 millimoles. That is our actual amount that we obtained. Now, if we take actual divided by theoretical times 100, we get a yield of 88%. Now, keep in mind, this is technically a crude yield, because this material has not been properly purified. Still, if this crude material is fairly clean, then an 88% yield is very nice. Let's look at the characterization data. Here is a TLC plate. I have 3 lanes on the plate. The left lane is the first crop, the right lane is the second crop, and the middle lane is a combination of both, a co-spot. This looks great. One spot by TLC. The mobile phase for the TLC plate was 50% ethyl acetate, 50% hexane. The solvent front traveled about 4.2 centimeters, and the spots ran about 0.9 centimeters. That is an RF value of approximately 0.21. How about the melting point? Our product, 4'-bromoacetanilide, is a common material and can be purchased through many chemical suppliers. According to Fisher Scientific, the melting point is 166 to 170 C. I got a melting range of 167.0 to 168.1 C. That's a good match, looking good. On the screen we have our full NMR spectrum with integrations. In total there are 8 hydrogens in the integration. 1 plus 4 plus 3. That's how many hydrogens we have in the molecule. Note that I didn't integrate these two peaks. These two peaks are from our NMR solvent, DMSO. The signal from the hydrogens on DMSO appear at about 2.5 ppm. Water in DMSO appears at about 3.5 ppm. So these signals are real, but they do not arise from our product. Everything looks good. No impurities in the baseline to speak of. The NH being next to the carbonyl and the benzene ring is pulled downfield to close to 10 ppm. The 4 aromatic hydrogens are right in the 6.5 to 8.0 ppm region. The methyl group is a nice singlet down around 2 ppm. Here's an expansion of the downfield region. On the far left is the NH. It's a bit broad, like many NH and OH signals are. The aromatic hydrogens show up as a pair of doublets, as is typically seen in para-substituted aromatic rings. Now we have the upfield region. Our methyl is on the far right. The other two peaks are from DMSO and water. Based on the NMR, TLC, and melting point, our product looks great. The 88% yield looks legitimate, and this reaction is a very nice example of an aromatic bromination. I hope you enjoyed seeing a demonstration of an aromatic bromination. See the description for links to supporting documents. Please subscribe, like, or leave a comment. Take care.